Great. Thank you very much for your time in this particular session today. So we're continuing with our discourses on probability. And in the past couple of meetings, we have considered several important theorems or principles that will enable us to capture probabilistic quantities, which is really what all of this is about. And we want to be able to do this at various levels, both at foundational levels and at abstract advanced levels. And so the kinds of theories and rules and laws and principles that we've looked at in the past are all geared towards helping us to be able to solve abstract and real world problems that can be characterized by some dynamics of occurrences. And that's where probability becomes very important. So to proceed, I mean, to continue from where we left off in the previous meeting, where we talked about principles such as the total probability law and Bayes theory, where we're trying to update from just a hypothesis into a hypothesis giving evidence, right? We want to consider the idea of the independence of events, right? Independence is a very important construct in probability, which you would encounter from foundational levels all the way through to advanced levels of mathematical statistics. Okay, so just from a philosophical or a conceptual standpoint, two events, let's say some A, and I'll just make some general illustrations before we actually start to write some formal theories down. Just like everyday language, right? When we say independence, so let's suppose that we have two events, A and B, right? In very simple terms, if you're independent, even as a human being, as a young adult, it simply means that you no longer rely on your guardians or your parents for your livelihood, right? You are able to take care of yourself and attend to your own life necessities without resorting to another individual for assistance, whether it's financial, emotional, or material assistance, right? So you are independent. That's why independence is also important amongst even nations, right? Nations have or win independence. Okay. I mean, Ghana was the first nation in the sub-Sahara to obtain its independence. Okay. Meaning that it's no longer relying on certain other parties for its well-being or for the welfare of its people. Okay, and there are several other nations as well that you can think about. So in general, some two events are, let's say A and B, are independent if the occurrence of one does not affect the probability of occurrence of the other. Okay, so for example, I mean, a die roll. If you roll a die and you get a 6 and it's a fair die, the fact that you get another 6 had nothing to do with the fact that previously you got a 6. If you have a coin, you toss it, you get a head now. Okay, at trial 1. Trial 2, you get a head. Well, you might want to call it a coincidence, but the fact that you got ahead in the first trial is not the reason why you're getting ahead for the second trial. So supposing that you do a third trial and you get another head, this is purely independent. You would go on and on and on, and at some point this would change, right? You might end up getting a tail somewhere. Of course, unless it is a rigged experiment, right? Or it's a biased experiment. And that's why you need to be careful about all these other lotteries and things like that. Oftentimes they are rigged in favor of the house or the owners, right? They are not, it's not like a fair coin or a fair die. If I were to put it in the context of a die, it means that the casino owner has rigged it in such a way that you will never be able to get, let's say, a 666. Or depending on how the game is structured, right? Because they own it at the end of the day, right? You're just a member of the public who walks into the casino house. So what do you know? You are subject to the whims and caprices of these game owners, so to speak, right? But yeah, that's just the general conceptual idea behind independence, right? The occurrence of an event not being affected by the probability of occurrence of another, right? But let's have a more formalized statement. Right. So that will be the very first definition for the meeting. So this is a formal definition. So this is supposed to be definition star, or let's say definition one for the day, right? So we can say that events the events A and B defined on the same sample space are considered independent. And when we say independent, we mean statistical independence. But normally we like to just drop off the adjective, okay, the statistical. But even if we don't say statistical independence and we just say independence at the back of our minds, let's know that we're referring to statistical independence. Okay. So two events A and B defined on the same sample space are considered statistically independent. All right. If the probability of the joint occurrence, if the probability of their joint occurrence, of their joint occurrence all right, is the product of their individual probabilities. All right. So this is we're moving away from the philosophical, understanding to a more technical definition that we can work with. So if you have some two events, A1, A2, or some AIs, but let's just be specific and look at the two case for now. A and B, and they're defined on the same sample space, right? Then they are independent if the probability of their joint occurrence is the product of their individual probabilities, right? And of course, when we talk about the probability of the adjoint occurrence, what do we mean? The adjoint occurrence can only mean what? So let's just visualize this. So I have my omega, which is the full, sample space, and I'm defining two events. This is A, okay, and B. Okay, so this is it. The joint occurrence happens here at the intersection, right? So in other words, by this definition, we're saying that the probability of this region should be the same as the probability of the whole of region A, multiplying the probability of the whole of region B. Okay, that's what the statement means. So thus, it means that the probability of A intersection B is the same as the product of their individual probability. So the product of A going into the product of B. Right? Now, just keep in mind that when the probability of A is greater than zero, right? So it's not zero, or it's greater than zero. And also the probability of B is greater than zero, right? And we have A and B being mutually exclusive, so they don't have an overlap. Then the two events cannot be independent. Okay, it means that they are dependent. So in other words, the idea of statistical independence is also by extension telling us about statistical dependence, right? So if we want to establish for any given problem, we want to establish whether some two events, and in some, as we move ahead, you will see that we can extend this to several other events, right? But now we're just looking at simple case, two events, right? So when you take the probability of the intersection and the probability of, I mean, the product of the individual probabilities, and they are not the same. That tells us that the two events are not independent, but they are what? Dependent. Okay, so that's just a side note. In other words, if you want to also prove dependence, it's just a matter of showing that the left-hand side is not the same as the right-hand side. Let's take a quick example here. Right? So consider a bag, right? Containing a bag containing, let's say, 10, right? 10 labeled, okay? And they're identical balls. So they all look, I mean, they have similar characteristics or same characteristics. All right. So a ball is, So let me rephrase it properly. So consider a bag containing 10 numbered identical balls, comma, of which one is selected, is randomly selected. Is randomly selected. All right. Then we want to now look at two, events. So, or two possibilities. Further consider the following events, right? So let me take this off. So further consider the following events. So we have event C. Right, so we have event C is, we have X such that X is less than or equal to 4. And then we have event D, which is defined as X such that X is even. All right. So we want to inspect, we want to investigate whether A and B are independent or they are dependent, right? So this is essentially what we will do. So what will be our sample space in this case? So here, so observe that our omega, right, from the problem, we're saying that a bag contains 10 numbered identical balls. So there would simply be what? Ball 1, ball 2, ball 3, ball 4, all the way to ball 10, right? So our omega would simply be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Now let's also enlist the members of C. All right. So C are all elements such that X is less than or equal to 4, right? Now, X being less than or equal to 4 does not mean that we can go from all the way to negative infinity up to 0 before we get to 4. It is in reference to the sample space, right? Whatever the event, you have to be defined on the sample space, right? So the sample space gives us the bounds. in terms of possibilities for whatever events that we can come up with. So x is less than or equal to 4, meaning that the least will be what? A 1. So C would be 1, 2, 3, and 4 inclusive. All right. And then how about D? Event D, we can also unpack it. And we're looking at what? Even values of omega. So that becomes 2, 4, 6, 8, and then 10. Right? Now here, of course, we're trying to investigate whether the probability of the intersection is the same as the product of their individual probabilities, okay? So that we can characterize it as independent or dependent, right? So the next thing we want to find is the C intersection D. So C intersection D would simply be what? This is going to be a 2 and then 4, right? So 2 and then 4. That is fine. So thus, if we want to find the probability, right? So thus, the probability of C intersection D, right? How do we find this? The probability of C intersection D would be what? The cardinality, right? The number of elements. So let's say the number of elements in C intersection D, okay, over the number of elements in what? Omega. Or here, because they're unique, we can also use cardinality, right? So it's the same as saying the cardinality of C intersection D over the cardinality of omega, right? And this is essentially going to be, there are 2 members here, and there are 10 members here, which is essentially 1 over 5. Okay, good. Now, however, let's consider the individual probabilities. All right, the individual probabilities. So we'll be looking at the probability of C, and then we'll multiply that by the probability of D. So we can say that further, or yes, so further, or on the other hand, the probability of C, okay, is given by the number of elements in C over the number of elements in omega. So this is going to be what? 4 elements over 10. Right? And then the probability of D is also going to be, D has 5 members, right? D has 5 members, so we have 5 on 10. Okay, hence the probability of C multiplying the probability of D is 4 on 10 multiplying 5 on 10, which is what? 20 over 100, right? 20 over 100, which is exactly 2 over 10. And this is also exactly equal to what? The probability of C intersection D. So this means that under this experimental scenario, the events C and D are independent. In other words, it means that when you pick a ball at random, whether the ball has a number less than or equal to 4 does not influence the probability that it would be even, and vice versa. Picking an even number does not influence the probability of getting a number that's less than or equal to 4. That's the general idea. All right. So therefore, A and B are, in this case, C and D are independent. All right. So let's move on to the next page here. So let's take another definition. Definition 2. All right. So here we're looking at events beyond 2. Keep in mind, in the previous definition, we talked about 2 events, A and then B. But like I said, in the real world, we would encounter a lot more problems than just 2. Okay, so what if n, the sample size, is greater than 2? So for the case of the sample size exceeding 2, okay, the events A1, all right, so the events AI, okay, where I is equal to 1, 2, up to n, right? This is simply saying that we have A1, A2, A3, all the way to AN. And we're talking of A1, A2, A3 simply because the sample size here is more than 2. All right. So for the case where n, or the sample size, is greater than 2, the events AI are mutually independent. Mutually independent. Okay. Yeah, mutually independent if and only if and only if the probability if and only if the probability of the intersection right? If and only if the probability of the intersection of any 2, 3, all the way to n of the events. Okay, is equal to the product of their respective probabilities. All right. So mutual, that's another way of saying independence when you have a lot more than two. Okay. So we're saying mutually independent. Okay. So these events are mutually independent if the intersections, okay, of any two, three, or all the way to n, of them is the same as the product of their respective probabilities. All right. So I think if you recall, so earlier, right, there was this identity that we talked about. So recall from earlier. So let me use this. Maybe red will do. Recall that this summation, okay, it's a very important identity. So when I'm summing n combination R, okay, and R is starting from 0 and going all the way to n. Right? If you're expanding, this is the same as n 0, right? Plus n, R moves from 0 to what? 1. All the way to n combination 2 plus n combination 3, right? All the way to n combination n, because R is moving from 0 to n, right? All right. So everything here collapses to 2 to the power n. This is a very important identity. The sum of n combination R from 0 to n is exactly 2 to the power n. So what does this mean? What's the implication for us? So thus, there are 2 to the power n, all right, minus n minus 1 of such sub-collections. Okay, of such sub-collections that should, okay, that should all be mutually independent. All right. For for independence of the n events to be justified. All right. That's just the whole idea. So basically the idea is that, you see, for when we say mutual independence, all right, it means that the probability of the intersection of any subset would be equal to the product of their individual probabilities. Okay, that's just what it means. So here, right, just to explain further. So it means that, for example, if there are so I have what here? I have AIs going all the way to AN, right? So I have events. So I have A1, A2, A3, all the way towards some AN. So there are a large number of them, right? Mutual independence means that, so mutual independence, it means that if I decide to take any of the subsets, right, I don't need to take all of them. So if I consider only A1 and A2, it means that the probability of A1 intersection A2 should be equal to the probability of A1 multiplying the probability of A2. All right. If I also decide to take the probability, if I want to take three subsets, right? So probability of A1 intersection A2 intersection A3. Okay. This should be the same as the probability of A1 multiplying the probability of A2 multiplying the probability of A3. Okay, so this can go on and on and on and on and on and on and on till the point where I can even take the probability of A1 intersection A2 intersection all the way to the intersection of some AK, right? And this should be equal to the product, right? So because of space, I'll just write it in the contracted form. So this should be the same as the product. So probability of the AI, okay, and we're taking the products, right? I moving from 1 up to K. So this is another way of saying probability of A1 multiplying probability of A2 multiplying all the way to probability of AK. So that's what mutual independence is, right? that any subcollection will satisfy this property. All right. Any such subcollection would satisfy this property. And we're saying that there are 2 to the power n minus n such minus n minus 1 such subcollections. Okay. And this can be, trivially established. But let me just quickly mention this, that we also have a concept called pairwise independence, right? Pairwise independence. Pairwise independence would mean that essentially when you take any two, so pairs, okay, is in twos. This condition is only true for any two, right? If I take them in turn. So for example, if I take the probability of A1 intersection probability of A2, it would be equal to the probability of A1 multiplying probability of A2. If I take the probability of A1 intersection probability of A3, it should be the product of their individual probabilities. If I take the probability of A2 intersection A4 or A3, that relationship should hold. Okay, so we have pairwise independence where independence is holding for any two, right? The emphasis is on two. Okay, whereas for mutual independence, we're taking the emphasis on any subcollection or any number of subsets. The relationship should hold, okay, for any number of subsets or subcollections. All right. So any two must be independent for us to get, pairwise independence. So the key thing to keep in mind is that mutual independence okay, implies pairwise independence. All right. But this is not the other way around. Okay, pairwise independence does not imply mutual independence. All right, so let's consider it this way. Let's look at pairwise independence. So now we know what independence is generally, right? Good. Now we can look at it from two perspectives. So we have the idea of pairwise independence. Pairwise independence. All right. What is pairwise independence? So this is just an aside. A set or a collection of some events. All right. Let's call them AIs. Okay, so let's say some A1. Of course, where I is moving from some 1 to n, right? But let's just unpack it. So the AIs are A1, A2, all the way to some AN. Okay. Is pairwise independence. All right. If any two, so here pair, so the emphasis on two. If any two events, and let's call them some AI and then AJ. If some two events, AI or AJ, they can be A1 and A2 or A3 and A4, A1 and A10. Okay, so AI and AJ. The most important thing is that I is not equal to J because we cannot, operate on themselves. It has to be operating from one to the other. So where the I is not the same as the J, because without this condition, then we'll be having things like A1 intersection A1 and or A10 intersection A10, which does not help our cause so much. All right. So any two events, AI, AJ, where the I and J's are unequal, right? Satisfy this condition. Okay, it satisfies the independence condition. So the prop of A, I intersection AJ is the product of their individual probabilities. Again, here the focus is on what? Two. All right, the focus is on two. Then for, I think I've written this already, but just for the sake of learning, let me repeat it, right? So two, mutual independence. So PI and then MI. Right? So here we can also say that a set, okay, of events so similarly, we have A1, A2, all the way to AN. Okay, all the way to AN is this time around mutually independent. I want you to note the statistical semantics here. You see, I'm not using the word are, I'm using is, and it might sound counterintuitive. You see, independence is defined on the set. Okay, that's why I'm using is here, not saying are. So in the case of pairwise independence, we're saying that the set of events. So we're referring to, though the set is made up of some other entities, which we call the events, right? But we're saying it is the set which is pairwise independent, and it is the set which is mutual independent. All right. Okay, so for mutual independence, MI, right? The set of events AI, okay, is mutually independent. Mutually independent. All right. But of course, in everyday conversation, you can say, A1 and A2 and A3 are mutually independent. That's totally fine. Okay. But of course, when you're writing it down, generally a lot more thought would go into some of these semantics, so to speak. All right. But I mean, these are trivial issues. So a set of events, A1, A2, up to AN, is mutually independent. Okay. If, so this is the distinction. If for any, all right, for any subset or subcollection. All right. If for any subset so here I can represent my subsets by, so if for any subset, so AI1, AI2, all the way to AIK, right? These are just subsets. All right. If for any, subsets like this, it holds that this relationship holds. The probability of AI1 okay, intersection AI2 intersection AIK is given by the products, okay, of the individual probabilities. So AI, so I now want to represent the 1, 2, 3 all the way to K. So let me call that maybe some J. AIJ, okay, where this time around J is moving from 1 all the way to where? K. All right, so that's the difference. So if you really look at it very closely, one is a weaker form of independence, whereas the other is a stronger form of independence, right? Mutual independence is a stronger form of independence as compared to pairwise independence, because pairwise independence is only satisfying for any two, okay? But mutual independence is taking any subset, so any two, any three, any four, any five, all the way to any K or any N, all right? So it simply means that mutual independence, so mutual independence would always imply pairwise independence. All right. Once there is mutual independence, it necessarily implies that pairwise independence is also established. But pairwise independence does not imply mutual independence, because any two can be independent, but it does not mean that it generalizes to all K or N elements. All right. So let's take a theorem here. So by this, we can say that I'm not sure what theorem this is. Is this the first for the day, right? So we can say that three events all right, three events, C, D, and then E, are independent, okay, are independent all right, if number one, they are if they are pairwise independent. If they are pairwise independent. If they are pairwise independent and two, this also holds. Sorry, I'm using A and B and C. So C, D, and then E. All right, so C, D, and then E. So these two must hold. So they must be pairwise independence, and the probability of all of the intersections must be equal to this. Okay, the product of their individual probabilities. Okay, so when this happens, it means that the three events are independent. Okay, and this theorem is very important because it may be tempting to have three events and then just think, well, if I want to establish whether these three events are independent, it's just a matter of checking whether the product of their joint occurrence is the same as this. When you do that, you'd be missing out some key information, and you may wrongly assume that the events are independent. Okay, for three events to be independent, they must be pairwise independent, meaning that the probability of C intersection D should be equal to probability of C multiplying probability of D. Probability of C intersection E should be equal to the probability of C multiplying the probability of E. And then the probability of D intersection E should be equal to what? The probability of, so you take all those possibilities, right? So there'll be, let's see, there'll be about three of them, right? C intersection D, C intersection E, and then D intersection E, sure. So for pairwise independence, it means that you need to check that those three conditions hold before this. So essentially, for three events to be independent, they must satisfy four conditions, right? The first three conditions are what we mean by what we're calling, or we're bottling up into pairwise independence. And then the fourth condition is pretty straightforward. All right. Now, not too long ago, I talked about the fact that for any given number of events where the number is greater than two, right, the number of such possible subcollections will be 2 to the power n less n minus 1, right? So just going back to this particular theorem, you can see that the three events, C, D, and E, would be independent if and only if all sub-collections, of the following conditions are satisfied. So let me break this down, right? I want to rewrite the same theorem, okay, but I want to unpack the second part. I mean, the very first part, okay, so that I use it to explain the other that I talked about. So thus, or if you like, equivalently, all right? So equivalently, the three events, all right? Equivalently, the three events C, D, and E are independent, or they are statistically independent. If and only if right? If and only if the following conditions hold, right? So we have what? Number one, the probability of what? C intersection D should be equal to the prob of C multiplying the prob of D, right? Number two, the prob of C intersection E is equal to the prob of C multiplying the prob of E. And then three, the prob of D intersection E should be equal to the prob of D multiplying the prob of E. And then finally, four, right? The prob of C intersection D intersection E should be equal to the prob of C, prob of D, the prob of E. Good. So for three events, four conditions need to be satisfied. So let's relate this to the previous remark that I made, right? That when you have n greater than 2 events, then there are 2 to the power n minus 1 such sub-collections. These are the sub-collections I'm referring to. Okay. So here, look at it closely. So thus, there are, and how did we arrive at this 4? Okay, the 4 is coming from, so going back to the rule, 2 to the power n, there are 2 to the power n minus 1 is equal to, so in this case, what is our n? our n is 3, right? Because there are 3 events. So there are 2 to the power 3 minus what? 3 minus 1. 2 to the power 3 is what? 8. 8 minus 3 is 5. 5 minus 1 is what? 4. So it means that there are 4 conditions, right? Okay. That must be satisfied. So in the future, for example, if you're given 4 events, right? If let's say you're given 4 events or you're given 5 events, and you need to establish whether the 5 events are independent, right? It means that you know that definitely you would have to check finally whether maybe even the probability of C intersection D intersection E intersection F intersection G would be equal to the probability of C multiplying the probability of D multiplying the probability and all the way to that. That one is definitely given, okay? But maybe you are not sure about all the other events, the possibilities that you need to check for, the conditions. This can help you find a number of conditions, right? So for example, if there are 4 events, okay, if there are 4 events, it means that the number of conditions I need to check for is 2 to the power 4 minus 4 minus 1. 2 to the power 4 is what? 16. 16 minus 4 is 12. 12 minus 1 is what? 11. So you need to check for 11 conditions. And one of the conditions would have to be the extreme case, right? The probability that C intersection D intersection E intersection F should be equal to the probability of C multiplying the probability of D multiplying the probability of E multiplying what? The probability of F. All right. Good. So there you have it, right? It means that this would necessarily be one of the conditions that you would check for. So once you check for this condition, that means you're left with what? 10 other conditions. And those 10 other conditions would have to be, you need to check for the probability of C intersection D, whether it's equal to prob of C multiplying prob of D. Then you look at C intersection E. So there'll be 10 remaining other conditions that you need to check for, right? You'll alternate the C, D, E, and F pairwisely. All right. If you're given 5 events also, it means that it's going to be what? 2 to the power 5, right? It's going to be 2 to the power 5. Okay, which is what? 32. 32 minus 5. Okay, you have 27. 27 minus 1 is 26. So you're going to be checking for 26 conditions. And one of the conditions would be the extreme case, that the probability of C intersection D intersection E intersection F intersection G will be equal to the product of their probabilities. So then you check the remaining 25 pairwisely. Okay, so that's the importance of this particular theory. Let's take an example here. Okay, so consider all right, let's consider this sample space. Okay, we have some omega such that for any given member, so X is such that you have X being less or equal 10. Okay, just similar to the previous scenario that we talked about earlier. Right? So once we define our sample space, we need to talk about what the various events. So let's consider these events. So consider this omega with events C. So I'm basically repeating the previous experiment, but I'll just be adding an additional event to it. Because if you recall, those were two instances. We just had an A and then a B, right? Or a C and then a D. But I want to add a third event to it so that we can explore how we can utilize this existing theorem, okay, to substantiate the independence or otherwise of this particular scenario, right? So we have this omega, and then we can define our C as the collection with X such that X does not exceed 4, right? Good. Then we can also talk about what D. D is the collection where X, all right, supposing X is even. And then let's define a third event. Let's call it C, CDE. And let me make this a bit, okay, so let's say X is such that X is equal to, I don't think I can fit in this space. So let me move to the next line. Right, so we have E is given by X such that X is equal to N plus 1 on 2. All right. We want to determine whether the three events are independent, okay, or otherwise. All right. That's the core problem that we want to establish. So that's the verification that we want to, perform, whether all the three events are independent or not. So in this case, what do? We need to start finding the various conditions, okay? And the good thing is we've listed them here. So I just need to do that, right? And so just to kind of start with, we would have to read lists the members, right? You recall that for the omega, it would simply be 1 all the way to 10. For the C, it's just going to be 1 all the way to 4. And then for the D, it's going to be 2, 4, 6, 8, and then 10, right? So it simply means that we So let me just redefine it here. So C, once again, C is, yes, just a second. We have 1, 2, 3, 4. One, two, three, four. We have B being 2, 4. Right? And then we also have a C. Sorry.
Please test.
Just hold on just a second, right? So we're defining our omega here. This simply is coming from the earlier problem of having a bag that contains a certain amount of identical balls, right? Which I used earlier on. And the balls here are numbered and they're identical. So essentially, if you go into the bag, you're going to see, let's say, ball 1, ball 2, ball 3, ball 4, all the way to ball 10, right? So if I'm defining my omega, it will just simply be a collection of numbers, right? So here, this is just a way of writing that omega is the set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But this is just the contracted form of writing it. Okay, this is simply saying that if I take any x, the x is such that it is a value less or equal to 10. Right? So the positive integer possibilities can only be numbers ranging from 1 all the way to 10. Right?
No. All right.
Good. Yes. So that's where it's coming from. So this is just our sample space that we're using for this particular context.
So,
yes.
So,
please
are you going to indicate that? Are you going to indicate that this is an integer or something like that?
Yeah. Of course. I mean, you mean the x, whether x is an integer?
Yes, please.
Yeah. That's a good point to make. Here, I haven't defined it because it is coming from a previous experiment, which was an experiment about a bag containing a certain number of balls, a bag containing 10 balls. So obviously, we know that the count is an integer. Yes, but supposing that we did not have anything about bags and balls or whatever, and I'm defining the omega, then I need to be a bit more explicit. So I'll say something like x belongs to z plus, okay, which is positive integers, such that x is less than or equal to 10.
Yeah.
That would have been the most precise way of stating this omega. But I did not do so because we're coming from a certain background where we know that the x's are counts of a certain number of balls, which is obviously positive integers.
Okay.
Yes, but otherwise, your intuition is definitely very accurate, right? What you are thinking about, the fact that you're very correct. In the ideal case where there is no background to the story, that's what we would have ideally done, okay, by specifying the number system to which x belongs. So in this case, it will be x belonging to the set of positive integers, less than or equal to 10.
Okay.
Yeah. Are you clear?
Yeah, yes, please.
Okay.
Thank you.
Yes, you're welcome. Good. So now we have our omega sorted out. We have our event C, which, I mean, again, this is also x here is by implication a positive integer. And then we also have our events D, where x is even. And then we've added, a third event E, which is the collection of all x's such that the x is equal to n multiplying n plus 1 over 2. All right. And here we will be having E. E will be, so what is our n in this case? What is our n in this particular case? Keep it in mind that n is oftentimes the number of events there are, right? So in this particular case, we should be looking at, so we'll have, in the first case would be, we'll have 1. Okay, if I take my n to be 1, right? If I take my n to be 1, then 1 going into 1 plus 1 over 2 is just going to be 1, right? If I take my n to be 2, I'd have 2 multiplying 3, which is what? 6. 6 over 2 is what? 3. Then if my n is 3, right? If my n is 3, I would have 3 multiplying 4. 4 over 2 is 6. And if my n is what? 4. Okay, my n is 4. So n here will be, so 4 multiplying what? 5 over 2, which is what? 10. So this will be my set E, right? And we know what the n's are. The n's are what? The if you like, the sort of the conditions, okay, that we need to check for. You know, there'll always be a certain number of conditions, and we get them by doing 2 to the power n minus 1. All right. The resultant value is what we're defining here. So the n is a growing value from 1 all the way to 4, depending on the number of events that you're looking at. Here, we're looking at 3 events. When you have 3 events, then you're going to have condition 1, condition 2, condition 3, condition 4. So that's how come I am substituting n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4 into this. And for every n that you substitute into this, it's going to give you a particular, outcome so that you can use it to define your E. All right. If instead of maybe 3 events, we define 4 events. 4 events, like we studied, there will be what? About 11 different conditions that we need to check for, right? There'll be 11 different conditions. So it means that our n will be a value that grows from 1 all the way to 11. Okay. So in the case of 4 events, it means that I'm going to substitute n is equal to 1, n is equal to 2, all the way to n is equal to 11 in order to derive my event E. Excuse me, right? But here the case is we have 3 events. So that's why we're doing what we're doing at the moment. All right, good. So the next thing we'll be doing, we want to verify independence. So we need to check all of these possible conditions, or conditions actually. So let's start one after the other. Let's try and find the probability of C and D. So now the prob of C, okay, which is basically the probability that of C and D happening at the same time, simultaneously, right? So if C and D occurs jointly, right, we've established previously that this would have a probability of 2 on 10. okay, which is basically 0.2. Right? But well, just for purposes of members of the class who may have arrived a bit late, let's kind of redo this from first principles. So we know that. So let's take the intersections first of all. So C intersection D, right? The intersection would simply be what, 2, 4. That we're taking. So just look at the side, okay, to guide us. So the next possibility would be C and E. Okay, C and E would also give us 2 on 10. I mean, 1, 3. And then D and E. Okay, D and E is going to be what exactly? That's also going to be 6 and 10. Right? And then finally, the extreme case, C into D into E. If we check, right, this is C, this is D, this is E. We don't have a value, and here we're looking at mutual intersection, not just sort of pairwise intersection, if at all you want to think about it that way. C intersection D intersection E is referring to a value that lies in each one of them. Okay, not just any two of them. This is different from union. For union, you can just be, if you are in just one of them, then you are in the union, right? You don't need to be everywhere. But for intersection, you need to necessarily be in one of them. I mean, in each of them. Recall your days of Venn, right? When you were drawing Venn diagrams and things like that. In the 3-part scenario, you still have that point of intersection, which is very small, right? Where all the 3 circles need to merge. So before you can be in that small pointed circle, I mean, that small part, right? You need to be in circle C, circle D, and circle E before you can be in that spot, right? So keep it in mind. I'm saying this because it's very tempting, for students to just assume that. So for example, in this case, we have C, D, and E, right? We're seeing one appearing here, one appearing there. So you start writing 1, you see 2 appearing here, 2 appearing there. No, it has to be in each and every one of the C, D, and then E, right? So if you look at this very closely, you can tell that there is no possible value that would be at the epicenter of all these 3 regions, okay? So therefore, the intersection would necessarily be what? Null. All right, good. So we and if the intersection is null, right, it means that the probability would also be 0 here. So since we've established the intersections, let's find their probabilities. So we have the prob of C intersection D. Okay, this would simply be the number of the cardinality of C intersection D as a proportion of the cardinality of what? The omega. So that's what? 2 elements over 10 elements. The probability of C intersection E, it would also be what? 2 on 10 the prob of D intersection E would also be what? 2 on 10. And then now the prob of C intersection D intersection E will be what? The probability of the null set, and that will be what? 0. All right. So now watch this. The goal of this exercise was to verify that whether the three events C, D, and E are independent. Okay, so we have done, I. So now we need to check whether this condition holds. All right. If we look at this very closely, the probability of C intersection D, okay, and if we take the probability of C only, the probability of C only will be what? 4 over 10. And the probability of D only would be 5 over 10, right? 4 over 10 multiplying 5 over 10, that's 20 over 100. And that's exactly 2 over 10. So if you check for each one of them, you would realize that these particular conditions, okay, 1, 2, and 3 will be satisfied for the most part. But that's where the temptation comes. You might think, oh, well, 1 to 3 have been satisfied. So then, of course, the 3 events are independent. Wait until you check for the final, the extreme case, right? Good. So let's check the extreme case here. So in essence, we can see that so the prob of C intersection D is equal to C intersection D C intersection E, and then D intersection E. All right. So this will be 2 over this will be the same as the prob of C multiplying the prob of D, which will be 2 over 10. Right? So condition 1 is satisfied. This would also be the prob of C multiplying the prob of E. Okay. Which would also be 2 on 10. Then the prob of D and E would also be equal to, that's if you take your time to check. This will also be equal to the prob of D multiplying the prob of E, which will also be equal to 2 over 10. But again, we cannot conclude yet. Let's look at the fourth condition, which is what? The prob of C intersection D intersection E is equal to what? We know this is, let's go back and check this. Okay, so we've computed the prob of C intersection D intersection E already, which is what? 0, right? Good. So now it means that I just need to find the actuals. Okay. Anyway, so I think I could have just maintained it. So the prob of D, the prob of C, intersection D, intersection E is equal to what? 0, right? But this is not equal to, look at it closely. This is not equal to the prob of A okay, which is the prob of A only is what? 4 elements over 10 elements, multiplying 5 elements over 10 elements, multiplying 4 elements over 10 elements, okay, which is equal to, I mean, something else which is not 0, right? This is 20 times 4, that's 80. So 80 over 1,000, which is 8 over 100. Okay. So 8 over 100, or yeah, some other reduction.
So please, I have a question.
So this could simply be, let's say, 2 over 25, something along those
So
lines.
please, I have a question.
Yeah, that's fine. So you can tell that obviously this probability is not the same as this probability. Okay. Yeah. Yes.
So please, I have a question.
Please go ahead. Yes.
So that 2 over 10, can you still break it down?
Of course, yes. But the point is, it doesn't make a difference, right? That we are interested in comparing whether our left-hand side and right-hand sides are the same, right? So I mean, you can break it down. That's still fine anyway. But the most important thing is that in fact, you can break it down. You can even write it in percentage terms or just in decimals, right? This will be 0.2, 0.2, 0.2. That's totally fine. This will be 0.4 multiplying 0.5 multiplying 0.4 or whatever reduction that works with you. Okay, but at the end of the day, the question is, is the product of the joint occurrence equal to is the probability of the joint occurrence the same as the product of the individual probabilities, right? That's the whole idea. So obviously, from this point, we can see that the events A, B, and C are not independent, okay? Because all the 4 objectives or all the 4 conditions have not been satisfied. Even if there are 10 conditions and only 9 are satisfied and 1 is not satisfied, that doesn't make it independent, right? All the conditions need to be satisfied. So hence, C, D, and then E are not independent. Okay. Yeah. Let's take a very simple you know, issue here. Let's take this theorem. So this theorem, I think 2, right? If C if event C D and then E, right, are independent, if these 3 events are independent, then it means that then E and C or C intersection D are independent. All right. So let's pay attention to this very well. We're saying that we have 3 events, C, D, and then E, and they are independent, right? So it's a supposition that we can make. These 3 events are independent. It's been established. So as soon as we say it's independent, it means that those 4 conditions have been satisfied, right? That's what that statement means. So if that is the case, then the events E and the event C intersection D are independent. All right. So let's look at the proof. Right. So by definition, right? By definition, we know that since the events C, D, and E are already independent, it means that, so by definition, and this was what definition 1, right? So by definition, we know that if they're independent, then the probability of C intersection D is equal to the prob of C multiplying the prob of D. Okay, good. So let me call this equation 1. Okay. Also, so again, by theorem, of independence of 3 events, we know that of all the other events that need to happen, that this event must also happen. So prob of C intersection D intersection E should be equal to the prob of C right? Good. So let me call this equation 2. So what does it mean here? If you look at this very closely, it means that I can write my equation 2, okay, in terms of equation 1, right? So thus, substituting 1 into 2, okay, it means that the probability of C intersection D intersection E is equal to, so this time around, instead of writing the prob of C multiplying the prob of D, right? I can write, because this is the same as the prob of C intersection D, I can just use the intersection. Okay, so this is the prob of C intersection D multiplying what? The prob of E. So in fact, right from here, you can even see the, the fact that C and, I mean, you can see the fact that the probability, I mean, yes, you can see that the E and C intersection D are indeed independent, okay? But if for some reason it's not clear, let's just go further. All right, so once I write this, okay, let's, all right, these are just stylistic choices that we're making. So let's represent this probability, okay? Or let us represent this Z, this event, C intersection D. Okay, let me call it F. Let F be equal to C intersection D. All right. So it means that the prob of C intersection D intersection E is equal to the prob of F multiplying the prob of E. All right. So now let's inspect this very well. What does this statement here mean? The probability of, so let me write this out clearly, right? I'm moving to the next page. So keep in mind that we're saying C intersection D is what? F, right? So it means that I can come and rewrite this part. So if I'm representing C intersection D by F, it means that here I have the prob of F intersection E, right? So hence the prob of F intersection E, okay, becomes what? The prob of F multiplying the prob of E. Okay. Thus, this simply means that, I mean, if this condition holds, it means that events F and E are independent. Okay. Where F is equal to C intersection D. All right. So there we have it. Let's take perhaps a final and let's see where that takes us to. Let's take another theorem. So theorem 3. So we can say that consider events C consider events C and D, right? Defined on the sample space S. Right? If the events are independent, then we can say that the conditional probability of C given D would be equal to the marginal probability of C. Right? Let's look at the proof here. So let's recall, by definition of independence, I mean, by definition of conditionality. Okay, so proof by definition, so by conditionality definition. Right, by conditionality definition, we know that the prob of C given D, right, is the prob of C intersection D on the prob of what? D. Right? But again, in the preamble, we've been told that the events C and D are what? Independent. So if they're independent, it means that we can replace the prob of C intersection D by what? The prob of C multiplying the prob of D. All right, so that's exactly what we'll do. So also by independence definition. Okay, it means that the prob of C given D is given by so since I'm stating independence, let me just, so by independence, this holds. Okay, thus the prob of C given D is the same as, right, the prob of C multiplying the prob of D all on what? The prob of D, which is the prob of C. Which is the prob of C. Okay, so that's it. You know, we've proved the theorem. And again, you see, it makes sense, right? Because if the two events are independent, right, then if we take the conditional probability, right, the probability of one event giving that other event, knowing very well that they are not dependent on each other, then it means that the conditional probability will just be the same as the marginal probability. It's almost as if there was no reference point or there was no given probability. Okay. So that's just the overarching idea that we just need to take a look at. Let's take a theorem. All right, just a couple more theorems, and then we should be able to wrap up. So let's just say that we have the following, right? So this is theorem 4. So we have consider events C and D. all right, defined on the same omega. Where the events are statistically independent. Events are statistically independent. Events are statistically independent. Then the following holds. Then the following hold. The following holds true. The first is so 1. So here we're going to be thinking in terms of complements, right? C, the complement of C and the complement of B are independent. 2, C and, sorry, this is supposed to be a D. So C and D right? C and D prime are independent. Okay, 3. C prime and D are independent. Okay. So what will happen is I would prove for the first case and I would add the 2, okay, the II, then the III to your assignment, right? I've given you one already, right? So just follow closely. You would have to prove the second and then the third case. So just watch how I'm going about the first case, right? Let's revisit the preamble. So we're saying that take 2 events, C and D, and these events are defined on the same sample space, omega, where the events, okay, the C and D are statistically independent. If this is the case, then the following holds true. So let's try to prove the very first one. Good. So the complement of C and the complement of D, I mean, yes, they are independent. So what exactly do we want to show? We apply the same principle. So we want to show that, or we want to find this. So we start with, if you want to find the independence, then we want to see whether the prob of C prime intersection D prime would, at the end of the day, we should be able to manipulate it so that this becomes the prob of C prime multiplying the prob of D prime. Okay, but we cannot just move from this argument to the conclusion. It doesn't, we need to justify, right? So first of all, note from set theory, okay, that whenever you have the complements of intersections, right? The complement of intersections is the same as, let me put it in a different way. When you take the complement of a union, it is the same as the intersection of complements, right? The complement of unions is the same as the intersection of complements. So now if I have, and vice versa, right? So if I have C prime intersection D prime, if I want to rewrite this, I can do so using unions. So this expression, C prime intersection D prime, is exactly the same as C union D all prime. Okay. I think this is what we call the de Moivre's theorem, okay, somewhere in set theory or so. Yeah. So we're just applying probability to it, so nothing changes. So we have C, so this becomes C union D. All prime. So let me use a square bracket for the probability. So I've not done anything new. I've just leveraged on our knowledge of set theory to just rewrite this expression. Good. Now, think about it. We also know, right? We've established this in class. This C union D, let's call it maybe some E, right? So essentially, I'm looking at the probability of E prime. Okay, we've established in class that the probability of a complement is the same as 1 minus the actual probability without the complement, and vice versa, right? So if I have the probability of A prime, it is the same as 1 minus the probability of A. Okay, so I'll just use the same idea. So this, okay, this right-hand side becomes 1 minus the probability of C union D. All right, good. Now, we also know that there is a rule that governs C union D, right? C union D, or in this particular case, the probability of C union D, okay, would always be what? The probability of C plus the probability of D minus the probability of the intersection of C and D, right? So let's do that. This is equal to 1 minus, so let me just open a big bracket here. So this will be the prob of C plus the prob of D minus the prob of C intersection D. Okay, so here obviously the minus would affect the component. So we have this is equal to 1 minus the prob of C, all right, minus the prob of D, okay, plus the prob of C intersection D. Okay, gradually we're moving. However, we've also been told, right? Let's go back. The C and D are already statistically independent, and we know what that means, right? If they're independent, then it means that the probability of C and D happening at the same time would necessarily be the product of their marginal probabilities. Okay, so I can further rewrite that step as 1 minus the prob of C, okay, less the prob of D, okay, added to the prob of C multiplying the prob of D. All right. Now here I can perform some isolations here, some factorizations, right? So think about it. This is 1 minus the prob of C. Okay, let me put this into some parenthesis. Then let's look at this side. I have what? Minus the prob of D plus the prob of C multiplying the prob of D. So I can factorize the prob of D out. Okay, so this is minus prob of D. Okay, and inside I would have, let's take a look at it properly. Yeah, so inside here, I'll be having what? Minus 1 plus the prob of C. Right? Yes. So this is minus 1 plus the prob of C. All right. But of course, I want this to look very much like this, so we can just apply, you know, the traditional factorization, and we can do that. So this is 1 minus the prob of C. And here, what can happen is the minus can move in there, right? So I can have plus the prob of D. Right? So plus the prob of D, I'll end up with 1 minus the prob of C. Okay, and guess what? This is actually equal to 1 minus the prob of C multiplying let's just check, you know, to make sure that everything we've been doing so far is consistent. So 1 minus this goes into the prob of C plus this minus the intersection. Yes, that's correct. So when we expand, we have 1 minus this, 1 minus that, you know, plus that. And here we have 1 minus the prob of C outside, okay, minus the prob of D, okay, plus this particular prob. So minus the prob of D here means that we should be having, yes. So look, I think there's an error here. Let's correct that. Because I already have minus prob of D here, this is supposed to be 1, not minus 1. Okay, so let's just correct that. Okay, good. So I have minus P of D here. So this is just going to be 1. Okay, and I already have minus, so this is will be my 1 minus the prob of C. Yeah, so that when you expand, you get the original statement back. So this means that we have 1 minus prob of C multiplying 1 minus what? The prob of D. Yeah, this is a very beautiful result. So think about it. If you look at it, so this is finally equal to, this is 1 minus the prob of C, which is basically the prob of the complement of C. Okay, multiplying the prob of the complement of D. So we've been able to show that the probability of C prime intersection D prime is exactly the product of the prob of C prime and the prob of D prime. Okay. Hence, we can say that C prime and D prime are independent. All right, so I can just leave you to think through and work out the second and then the third parts, right? So apply your set theory argumentations, and I think you should be able to solve those problems.
Hello, sir.
Yes.
Sir. Sir, please said you proved the second one for us. Then all of them are.
No, I said I'll do the first one, and then you take the two. Right? So if you've understood the process, the argumentation, the way we moved from this side all the way to this side, you should be able to, as a matter of necessity, handle the, the I and then the I. Okay? Yes. I can hear you.
When we are done with that, when we are done with that, can you send us the video?
Good. Let's take this other theorem. Right? So this is supposed to be theorem, I think theorem 4 or 5. Right? So theorem, this is theorem, let's see. Is it so theorem 5, right? Good. So theorem 5. Right? We can say that consider. It looks like there's a lot of considerations, right? Yeah. So let's consider independent events. Consider independent events A1, A2, all the way to AN. All right, with corresponding with corresponding complementary events. So now we have the events and then their complements. So with corresponding complementary events. All right, then it is true, right? Then it is true that the prob of A1 union A2, okay, union all the way to union AN, all right, is equal to 1 minus the prob of A1 complement multiplying the prob of A2 complement, okay, multiplying everybody that's available all the way to multiplying the prob of AN complement. Right? This is a very beautiful theorem. Okay. So we would prove this. Keep in mind also that maybe I should have written this before the theorem 5, but just note there's also another theorem, right? We'll be coming to prove this theorem 5, all right? But just note as a theorem, or it could also be a corollary, all right? But so let's make it, let me make it theorem star, okay? It's an important statement to make. The idea is that if you have any events which are statistically independent, then their complements are also necessarily statistically independent, right? So let's just put it down. So if the events A, A1, A2, all the way to AN, right? Defined on omega are statistically independent. And at this point in time, we are masters of all kinds of independence, right? We know the weaker and then the stronger forms of independence and the various conditions they need to satisfy in order to be established. So defined on omega are statistically independent. Then we're saying that necessarily the complementary events the complementary events or the complements, right? The complementary events, right? And what are these events? A1 prime, A2 prime, all the way to AN prime, all right, are independent. All right, they are independent. In fact, this can be proved. All right, so let me add this to the, the uptakes that you need to consider, right? So giving the events A1, A2, all the way to AN defined on some omega, and given that they are statistically independent, show that their complements are also independent. But like I've told you, all of these proofs, though we are proving them and all that, but they also, we call them theorems for a reason, right? These are established principles. So when you encounter a problem, you should be able to recall these theorems. Sometimes the ability to move from one step to the next step is because of a theorem that you remember or that you can invoke, right? Mathematically, before you can move from any step to the other, you need to have a justification. You can have a step, I mean, like you're climbing a mansion or you're descending from a castle. In the real world, you can just take, steps, but in the mathematical world, you cannot just descend and come down, or you cannot just climb and go up. What is the basis for which you are taking the first step? Okay, now you are step 2. What is the basis for which you're moving from step 2 to step 3? And the basis are grounded in and on these theorems, right? So as we're proving them, make sure that you keep them in mind as well, all right? So that you can use them to, it makes you very flexible. You're able to manipulate your way legally to solve, all manner of problems. Okay, so you can work on this proof, right? So let's say that proof so to be delivered, right? So please add this as well. So let's go back. Yeah, so to be delivered, there's also to be delivered, right? So now let's prove this theorem, the theorem 5, right? Ideally, I would have left it to you as well, but hey, let's just do that quickly. So consider independent events, A1, A2, all the way to AN, with corresponding complementary events. Then this is true. Okay, then this is true. So let's do that. So proof of theorem 5. Proof of theorem 5. Right. So now, the proofs build on each other. So before I start, I know that this theorem is true, right? That if you have any statistically independent events, their complement would necessarily be true. I mean, would also be independent. Okay, so I can start by saying that by by theorem star, right? By theorem star, it means that though it hasn't been mentioned in the preamble, but I know that by some theorem, independent events have their complements also being independent, right? So that gives me a shortcut. So by this theorem, we can say that the events A1 prime, A2 prime, all the way to AN prime, okay, are independents. Right? Okay, so what does this mean? If they are independent, then it means that, right? If they're independent, it means the probability of their unions should be the same as what? The probability of their, the probability of their intersections should be the same as the product of their probabilities, right? So this is it. So this means that the prob of A1 prime intersection A2 prime intersection all the way to A and prime is equal to the prob of A1 prime multiplying the prob of A2 prime multiplying the prob of AN prime, right? That's what it means. Okay, now we can also apply, some of our existing theorems, okay, which we've looked at in the past, all right? And so we can say that, say for example, that if that's the case, then we can write those probabilities as certain. In terms of their complements, all right? So that's exactly what I mean. So we can say that, but, or recall, all right? However, we know that the probability, right, of A1 union A2 union all the way to union AN, all right? We know that at the end of the day, this is, right, the probability of unions is the same as 1 minus the probability of the various intersections. all right? But specifically, this is what I mean. So this probability, okay, plus the complements, right? Any probability plus its the probability of any event plus the probability of the complement is what? Is going to be 1, right? The probability of A plus the probability of A complement is what? 1. So here, the probability of this plus the probability of A1, okay, the probability of A1 union A2 union all the way to union AN, okay, prime. Okay, this should be equal to what? 1. All right, the probability, let's call all the unions maybe D. So then the probability of D plus the probability of D prime is just 1, right? But here, this is the trick. I'm going to use this to get to where we need to be. So this implies that the probability of A1 union A2 union all the way to union AN, right, is also what? 1 minus the prob of A1 union A2 union AN prime, right? Good. Now this, see, I'm taking the union of the complement of the union, right? So this is equal to 1 minus the complement of a union becomes the intersection of complements, right? So this becomes 1 minus the probability inside. Okay, so I will turn them upside down. So I have now A1 prime intersection A2 prime intersection going all the way to intersection AN prime. All right. And there we have it. All right, let's take a look at the proof. So we need to show that giving the independent event A1, A2, all the way to AN with complementary events, okay, then it means that this is true. Okay, so maybe there's just one final step. Obviously, because the AIs are independent, okay, it just simply means that here, the probability of all these intersections can be written as a product, right? So this is equal to 1 minus the prob of A1 prime multiplying the prob of A2 prime multiplying all the way to the prob of AN prime. Okay, so basically we've shown that we've shown that the prob of this union right? The prob of this union, I moving from 1 up to what, n, right? The prob of this union of AI is given by is the same as 1 minus the products, I moving from 1 up to n of the probability of AI prime. All right. Let's just take this quick corollary. All right. So just giving this, you realize that all the various events may have different, they have different probabilities, right? Here, the prob of A prime, the prob of A1 prime, prob of A2 prime, and all that may not necessarily be the same, right? They would have different probabilities. So that's why we, in statistics, will say, you would come across this term a lot, IID, independent and identically distributed. Okay, independent is what we're talking about. Identical distribution means that they have the same, they come from the same probability distribution, right? So they have sometimes they have identical probability. Okay, another way of wanting to look at it, right? So let's just take this quick corollary, okay, from this point on. What would happen if these probability of AI primes are all the same? Okay, this will happen. So corollary. Right? So if all the events, so I'm just wrapping up. So if all events, A1, A2, all the way to AN, okay, bear the same probability P. Bear the same probability P, then the probability of the union from 1 to n, okay, of the AI, okay, will be the same as so here, this is it, right? The probability of the complement are what? The failures, right? The probability of success is P, the probability of a failure is 1 minus P, which is Q, right? So we have this is going to be 1. This 1 is coming from the already existing 1. And these are what? Products of failures. So failures raise the power, failures multiplying themselves n times, right? So 1 minus failures. The failures are 1 minus P, okay, the complements multiplying themselves n times, which is 1 minus Qn. Right, so this is the case where they all are identically distributed. Okay, good. Now let me finalize the meeting by just once again trying to establish the difference or the distinction between mutual exclusivity and then independence of events, right? Though they have a few things in common. So let's just say that mutual so we have mutual exclusive events. So this is the final thing that we're handling. Mutual exclusivity. And then statistical independence. Statistical independence. Right. So the first case, they're all trying to answer the question of what is, a certain probability. So the first observation that we all need to make is that the prob of A intersection B would always be 0. Okay. But here, the prob of A joint B is the prob of A multiplying the prob of B. 2. The prob of the union. So A union B. All right. If they are mutually exclusive, this will be equal to, it means that the probability of the intersection is 0. So this would simply be the prob of A plus the prob of B. But here, guess what? For statistical independence, the probability of A union B, okay, would be the prob of A plus the prob of B plus, you see, because of this, right? Sorry, minus, right? Normally we would take minus the prob of the intersection. Here, the intersection is 0, so nothing comes here. But here, we can write this probability of this intersection as this. All right, so this is minus the prob of A as a product of the prob of B. All right, good. Then 3. We can also take the conditional probability. The prob of A given B. We know that by definition, it is what? The probability of A intersection B over the probability of B. But guess what? That probability of the intersection is 0. So the top will be 0 and the entire value will be what? 0. So it means that for mutual exclusive events, the conditional probability would always be 0. Okay, whereas for statistically independent events, right, the prob, the conditional probability of A given B, right? Think about it. The top is supposed to be the probability of A intersection B over the probability of B. But the probability of A intersection B is given by the prob of A multiplying the prob of B. So this divided by the prob of B would simply give you what? The prob of A. Okay, good. And then finally, the fourth characteristic. Well, I mean, we could throw this in. You can verify that the prob of A, right, given the complement of B, okay, this would be equal to the prob of A on the prob of B prime, right? Okay, so you can verify this, and then similarly, or I mean, on the other hand, when it comes to statistical independence, the prob of A given the complement of B, okay, we can show that this would always be the prob of A. All right, there are several other characteristics we can look at, but these are just a few. Okay, so mutual exclusivity and statistical independence have some, I mean, they are philosophically, they have a thin line separating them, but it's thin, but it's a very important and significant line as well, right? They are not equal. Okay, so for every quantity that you choose to compute, for every probability quantity, mutual exclusivity would give you a different value from what statistical independence would give you. All right, good. So just a quick recap of everything that we've done. Right, so I think we actually started the conversation with, yes, independence. We've talked about what independence is in general, and most importantly, the fact that there's pairwise independence and there is mutual independence, where mutual independence means that when you take any of the subsets of events, the traditional independence relationship has to hold for any one of them. So whether you take n to be 2, n to be 3, n to be 4, or n to be n, that equality of the probability of the intersection being equal to the product of the individual probabilities needs to hold consistently. Whereas for pairwise independence, any two, right, should have those, that condition holding. That makes pairwise independence a weaker form of independence. When we say weaker, we don't necessarily mean it's not useful. No, weaker as in when you have pairwise independence in the relationship, it does not mean that you have mutual independence. That's just what we mean by it's weaker, right? However, mutual independence is stronger because once you establish mutual independence, it would imply pairwise independence. So in the future, if you're given a scenario and you're asked to prove for, let's say, pairwise independence of the following events, if you're able to show that they are mutually independent, it means that you've necessarily proven that it's pairwise independence. Okay, but the converse is not true, right? So we've looked at some theorems governing pairwise and mutual independence. Yes, a lot more other theorems that you've had to look at. And here, the key consideration to keep in mind is the idea about the number of conditions to check for or sub-collections, right? We've looked at 2 cases, 3 cases. In the future, you can be given 5 cases, or in the real world, you're working with 10 cases. The number of conditions that need to be satisfied for the events in question to be independent would be different, right? There will be a lot more. And that number, the number of conditions you need to check for, would always be the order of 2 to the power n less 1, right? And I've looked at, a numerical example to show how we verify independence. And from there, we've continued to look at some other theorems where if you have three independent events, then we can say that one of the events and the intersection of the remaining two will necessarily be independent. And we've established that rigorously from here. And we've continued to look at the fact that if you have two events defined on a certain sample space where they are independent, then necessarily the conditional probability of one given the other would simply be the marginal probability, right, of the main event. Given two events, okay, where the events are independent, the following are true, okay? And I've showed the very first one, and you need to work out the second and then the third, right? There's also a theorem that we've just looked at. But before that, we said that a very, very simple but important theorem to keep in mind is the fact that if you have any independent events, their complements are also independent. I think it's a very beautiful and remarkable statement to keep in mind. And I've asked you to also establish the proof thereof. But we can use that idea to prove that for any independent events AIs, the probability of their unions would be the same as the complement of the product of the failure probabilities, right? Or better still, the product of the unions of the AIs would be the same as one less the complement of those AIs. Another way of thinking about it is this: the probability of the unions of independent AIs is the same as the complements of the complements of the AIs. I'm saying complement of complement because this is already complement and we are taking the product and I'm doing 1 minus. So 1 minus is actually giving me the complement of the product complement, right? And, we've looked at the case where what if the probabilities are identical? They're the same, right? It means that then the product of their unions would actually be 1 less the failure probability to the power n. And these are, this is just like a summary of the distinction between mutual exclusivity and statistical independence. All right. So I look forward to the very next session on our conversations on probability in mathematical statistics. Thank you very much.